I want to talk today about how shear strength parameters are determined through testing, laboratory testing. Recently we've been talking about once you determine the stresses on an element of soil, you can how to manipulate it and figure out what the stresses on different planes are and stuff like that. And we also talked about how we determine these Moore failure envelopes, but we didn't go into the testing and how we actually determine what failure is and and kind of the setup of the test that we use to determine the Moore circles using to determine the failure envelope. The first test we'll talk about is called the direct shear test. And I've drawn the setup here on the board. I'm going to go over it really quick. What it is there's a fixed base, which is this bottom section. And this is a cutaway view, but it's an elevation view. So this is bottom, top, and it's just a cut right in the middle of the test. So you have a fixed base, and then you have a movable top ring. So what happens during the test is this stays still, and this would slide this direction. And what you're doing is you're forcing the failure plane horizontally through this soil specimen, which is right here. The test is run saturated, and you have porous stones on the top and the bottom, which allow for the test to drain during your test. And this piston on top, that's so you can apply normal force to your specimen, and that way you can get different stress states and figure out that failure envelope. So let's see, what you do during the test, you'd measure your shear load over here, which is your force which you're requiring to push this top part and shear the specimen. You measure your horizontal deformation, which is which is the deformation you had to push this to shear, and also your vertical deformation, which is the movement of this piston up and down as the specimen shears. And this is just an elevation view. But this over here is the top view of it, and what you're looking at is you now see this circle in the middle is the specimen. So you're really looking at a circular specimen, and we'll talk later about nominal area, and that's just the area of the specimen where the shear plane is being forced through. Okay, I want to talk about when we're running these tests, what we're actually measuring. There's a few things. We talked about the shear load, the horizontal deformation, and the vertical deformation. So when you run these tests, you can plot up the results. And we'll have delta here, which you remember is the horizontal deformation. And up here we'll have shear strength, or the shear stress. And what the shear stress is the shear load divided by that nominal area we talked about earlier. So this is really just P over A. That's the shear load divided by the nominal area. So what happens for a test is it starts off at 0, of course, because there's no shear load if there's no shear force, or there's no displacement also. So what happens is this test will increase to a certain point, it'll peak, and then it'll drop off and then assume some residual strength. And if you run this test at a variety of normal forces, you're going to get a variety of peak shear strengths, because the shear strength is always a function of the normal force. So you may get one that's up here, here, maybe one that's even higher, up here, peaks out, and then follows like that. Okay, so you have these shear stresses for what you induce with your shear load. But you need to figure out the normal force as well. And I'm going to say this is we'll call this sigma, we'll call it sigma normal 1. And that's just the one just differentiates it from the first, second, and third test. So for sigma h1, it's the normal force, which is P, and that'd be P1 for test 1 divided by that nominal area that we talked about earlier. And it's the same for the rest of these tests. Sigma n 2 equals P2 over A, and sigma n3 equals P3 over A. Okay. So now that we have these values, I'm gonna go ahead and sign these also over here. So we'll call this peak tau 3, and that corresponds to the sigma 3. This is tau 2, and this peak will be tau 1. Okay. So now what you have is you have a variety of shear stresses and normal stresses. I want to point out one thing before I move on about this behavior where it peaks and then comes back down. If you remember back to your Physics 1 course, there's a thing called dynamic friction and static friction. And dynamic friction is always lower than static friction. And this is similar behavior to what we're seeing here. Nothing's moving up to here. We're getting a little bit of displacement, but it's not a whole lot. And then once it hits this peak, that's kind of like your peak static friction, and then it starts to move a lot, and then it drops off, and you have less strength, and that's just like you have less frictional force because you're now in the dynamic mode where things are moving. But okay, regardless of that, now we have shear stresses and normal stresses. So from before, so I'm going to leave that up here. I'm going to go ahead and get rid of this. So what we've been looking at is for the Moore plot is a plot of shear stress versus normal stress. So we have the points now. So let's go ahead and make one of those plots. So this is normal stress, and this is shear stress. So I'm just going to plot values here that are approximately corresponding to what we have there. See, we have tau 1, tau 2, and tau 3. So tau 1 is sigma 1. See, sigma 1 is the lowest, and tau 1 is the lowest. So we'll call this sigma 1 or sigma n1, and we'll call this tau 1. So that plot's here. And let's say sigma n2 is about there. Tau 2 is about here, so maybe right there, and then we'll say the sigma n3 is about there, and maybe tau 3 is up here. So after we plot this up, what we do with the points, you connect them with a line. It's more Coulomb envelope, and what we have here, that's your friction angle. And if you have any intercept here, that would be your cohesion. But a lot of times these are running granular soles, and there's not a lot of cohesion intercepts for this type of test. Let's see, getting ahead of myself. Okay. Yeah, actually that's about it for the data reduction of this type of test. So that's what you do. You run different tests, and you run them at different normal stress levels, and that way you can determine how the shear stress varies with normal stress and figure out your failure envelope. But I talked earlier about how we also measure the vertical deformation, and I'm going to show you how that plots up and talk about that a little bit, and talk about how soles respond to shear environments. So we have see, I'm going to plot the okay. So talking about delta H is your change in height, which is your vertical displacement. So that's what's on this axis. And then we're going to plot that with respect to delta, which is your change in, that's your horizontal displacement. So initially, what we're going to see is a little downward movement from this from that top plate. It's going to move down a little bit, and then at some point it's going to start moving up. And then at different stress levels, it responds differently. See, we have, what we'll call that one. Let's see which number test that was. That was sigma H3. So that's the one that we had the highest normal stress on that test. Sigma H2 looks something like that. And sigma H1 something like that. So what you're seeing here is for the increasing normal stresses on the sample, you're going to get a decreasing change in height as we shear the sample. But what you're seeing here, you have kind of a negative, what's called dilation, and that means that that's the change in volume of the sample as it shears. And what you're seeing here is if you have particles, being sheared, your particles are not in their densest configuration to begin the test. So initially, when you move these couple particles, they might get slightly denser, and then your volume is going to shrink. So that's what you're seeing here. But as you continue to shear, so now you're in a dense configuration, a fairly dense configuration. And as you continue to shear, what happens is these particles move from something like this to something like this. As the particles roll past each other, initially they're sitting here, and then when they move to this configuration, they roll past each other like this, and then it increases the height, and it also increases the pore volume of the sample. So this is why when you're walking on the beach, and so you're walking on some saturated sand. See, this is your foot. It's a really bad foot. But this is why. You're walking on the beach on some saturated sand. And as soon as you step down, you notice this circle forms not far in your foot. And it's dry, or it appears drier than the surrounding soil. What's happening here is when you step on that soil, you're shearing the soil around your foot. And you're moving from a dense configuration to a looser configuration, and since the particle volume can't change, you're changing the pore volume, and you're increasing the pore volume, which means you're increasing the places for water to flow. So therefore the water no longer sits on top of the sand surface like it is around here, and it soaks into the extra pore volume created by shearing the soil. There's one more key thing I want to talk about with this direct shear test. One of the major disadvantages of running this test is that during the test, we talked about principal planes earlier, but during this test, the principal planes are allowed to rotate. They're allowed to rotate uncontrolled, which is not a very good make sure this camera's looking at me. Okay. It's not a very good representation of what you're actually seeing in field loading conditions. So, let's see. I'm going to go back to some soil elements. Just draw a couple here for you. So this is going to be the initial state of what we're seeing. Okay. So initially, you have some load. That was that P, which is on top of the sample, and we're just going to go ahead and call that sigma 1, just for simplicity, from what we've been looking at. And you've got a sigma 3, which that's equal to K naught sigma 1, just because it's that's basically the horizontal pressure on that sample. Okay. So if you want to plot this on a Moore diagram, you have tau and sigma, and you have sigma 3 here, because that K value is less than 1, and you're going to have sigma 1 over here somewhere. And you got some Moore circle. And what you're looking at is you have sigma 1 and sigma 3 are principal planes because there's no shear stress on either one of those planes at this time. So that's your initial state. But as you shear the specimen, we're going to come into the final state over here as to what you see. Remember, we induced a failure plane that was horizontal. So now we're going to have shear stress on the horizontal plane. And that's going to be, and since this is the element of failure, that's going to be tau failure on the failure plane, because the failure plane is that horizontal plane and it's at the failure condition. So we're going to have that. We're going to have shear stresses now on both of these initial planes. And this is still sigma 1, that didn't change. And this is some sigma 3 now. But those are no longer principal planes. So let's look at how the principal planes change during the test. So we know that let's call this tau FF. Let's just say it failed here. So we know one point on our circle, our failure circle, and that's that sigma 1 tau FF, because tau FF occurs at this stress level. So that's what this point is. Sigma 1 tau FF. Okay. And if we're going to go with a more Coulomb failure theory, we're going to assume it's a granular material for this example. We have the failure envelope goes from 0, because it's cohesive material, through that point. Through that point. And that point represents where one of these circles touches the failure envelope, because that's the definition of the failure circle and failure envelope from the Moore Coulomb failure theory. So I'm going to try my best to have this look good. Okay, that's not too bad. All right, so now we can graphically figure what these stresses are, but for our purposes, this is sigma. This is now sigma 1 failure, and this is sigma 3 failure. And that's your principal stresses of failure. But we need to figure out how they rotate. So we need to figure out where the pole of this Moore circle is. So we know that the pole is the point where all stresses in the planes they act on intersect the Moore circle. So we know that this sigma 1, which hasn't changed yet, is acting on the horizontal plane. So where this intersects the Moore circle is the location of the pole. So So we have a point here, draw a horizontal line, and it intersects right here. So that's your pole. And since this pole is the intersection of all planes and the stresses that act on them, we can show where sigma 3 and sigma 1 act now. So sigma 3, if you draw a line from the pole to sigma 3, that's the plane that sigma 3 acts on. And this is the plane that sigma 1 acts on. So the rotation of the planes can be found by solving for that angle. We'll call it theta 3, just for the sake of being the sigma 3 plane. And then this angle is going to be, we'll call that sigma 1. Theta 1 for the theta 1 plane. So as you can see, throughout the test, the principal planes go through some rotation, which is not really indicative of the field conditions that we're seeing. So that's one major disadvantage of this test. But a couple of advantages are that it's a really quick test, it's pretty cheap, and it's a very simple test. So that's and it gives fairly good results and good estimations of the shear strength parameters. That's some good advantages of it. But some disadvantages, like I said, you have this rotation of your principal planes. Let me draw something real quick to illustrate this. But when you have stress concentrations too, that's a bad thing at the boundaries. So if you're shearing this specimen in here, which I had up earlier, so you're shearing this specimen, and these are pretty small. These things are only a couple of inches in diameter and maybe an inch or two high. So when you shear this thing, you have stress concentrations of these boundaries that are not seen here. So you have non-uniform stress distributions throughout the sample. So really what you're seeing is a kind of an average shear stress, and not really what the peak is in the sample, because you have all these. It's a non-uniform stress distribution. And also, one of the big major disadvantages is you're forcing failure to happen through a horizontal plane, which may not be, the plane that failure would occur in if you were to see it in the field. There's a lot of things that determine where that failure plane is. There could be a weak slip plane. These might not have the same properties horizontally and vertically or all direction. They're not isotropic materials. So that's one thing that is kind of a disadvantage of this test. But it depends on what your sample is. If it's some clean, fairly uniform grain material, then that's probably a good estimation of that.